Hey, this is Chapter 9, Inferring Population Means. Just a quick review of things that we've covered in the past and how it connects to Chapter 9. So if we're interested in finding out some information about a population, maybe we would collect data with a sample and then calculate a statistic. If the data we collected was binary, then the statistic we'd calculate would be a proportion, or p hat. Whereas if the data were continuous, then the statistic that we would calculate would be our x bar. We're going to use one of these statistics to make an inference about our population parameter. So about our population parameter. So if we calculated a p hat, what we're going to be doing is inferring about our population parameter p. But if our data, we calculated an x bar, then we'd be making an inference about mu. So in chapters 7 and 8, we spent time talking about how p hat behaves and learning about the shape and distribution of our p hat. That was the sampling distribution of p hat. And we used that to make inferences about our population parameter. In Chapter 9, we're going to focus our study on x bar. How does the distribution of x bars behave? And once we know that information, we'll be able to make inferences about mu. So, whenever we draw a conclusion about a population based on observations from a sample, we're making an inference, so that's inferential statistics. And when we make that inference, we can never be absolutely certain of our conclusions. But since we know how our statistics behave, we're able to measure how certain or uncertain we are. So the next thing on our notes is a little table that is kind of similar to what I was just talking about. So here we are in Chapter 9. We're going to be focused on our sample mean. That's our x bar. And we'll be able to make inferences about our population mean, mu. We'll also be using our sample standard deviation, S, and our population standard deviation, sigma. So we want to keep those variables and symbols in our mind. So when measuring the quality of a sample, we'll be interested in evaluating the estimation or sampling method used, not just a single estimate from a single sample. So, just like in Chapter 7, we're going to want to consider, are we able to generalize our results to a larger population? And can we quantify how far off our estimate is likely to be? So to answer these questions, we're going to have to understand the behavior of our statistic, our sampling distribution, and we will want to know, was our sampling method accurate? So that's talking about our center. And how precise was our sampling method? In other words, how spread or how varied do we expect to see our sampling distribution? So together, our bias and our precision are used to quantify the uncertainty in our inferences. So that's just another way of talking about our center and our spread. So the sample mean, which is x bar, will be our outcome of interest in this chapter. And we'll be learning about the probability distribution, and it's going to be called the sampling distribution of x bar. Again, it's a sampling distribution because x bar is a statistic from a sample, and we're going to be using it to make inferences about our population parameter. So to get started, like in Chapter 7, we are going to use some simulations to learn about the behavior of our statistic, of our sampling distribution. And so let's consider a group of mothers that we've seen in a previous data set to be our population. So the population distribution is shown below. And so here we are looking here. And notice that along our x-axis here, we have it labeled mother. That's a good indication to remind us that our observational unit for this is mothers, or mother. Our N is 1,375. And the other two pieces of information here, we have mu, because this is our population, is 62.45, and sigma is 2.355. So again, this summary statistic is really about the population because we're going to be sampling from it. So we're going to simulate what would happen so we can learn about X bar. So a couple things. We can notice that it's unimodal and symmetric, and you can see the red overlay of the normal distribution, so you can see how closely it follows the normal distribution. So we would say that this is normally distributed with a mean of 62.5 and a standard deviation of 2.4. Now let's talk about the simulation that I'm going to do. So we're actually going to run 3 separate simulations, and in each of them we're going to look at 1,000 samples in each simulation. So the first simulation, so I'm right here looking at simulation number 1, we're going to have 1,000 samples of n equals 10. Okay, so the sample size in each sample is 10. So 10 mothers were collected, and the average height of those 10 was calculated for each sample. So we can see here that the summary that we have is talking about the summary of our samples. So now our observational unit for this simulation is really a sample of 10 mothers. So each point that was plotted for this histogram, or that was like looked at for the histogram, is the X bar for 10 mothers. So in other words, we sampled 10 mothers, and then we calculated their X bar, their average height, and then we collected 10 more and calculated the X bar, and we kept doing this until we ran it 1,000 times. So we had 1,000 samples, each with 10 mothers in it, and calculated all those X bars. And then we plotted the histogram of these X bars. The average of these X bars, so if you were to average up all of these things, it's recorded right here. So the mean here is the average of our X bars. And the standard deviation is the standard deviation of all these X bars. And notice now our standard deviation is 0.736. It's much smaller than the population standard deviation that was 2.4. However, we also can notice that the mean at 62.46 is really very similar to the population mean. So that's our first simulation. Let's take a look at our second simulation. Again, we ran it 1,000 times. This time, we took a sample of 25 mothers. So again, the observational unit is a sample of 25 mothers. And again, we took one sample, 25 mothers. We took the average of those 25 and recorded it. That was our X bar 1. Then we took a second sample. We have 25 mothers, found their average, recorded it. And we kept doing that 1,000 times. And so we had 1,000 different averages that we averaged together to get this mean. And we also looked at the standard deviation of all those averages. And so now our mean is still centered at 62.4. So very similar, but our standard deviation's a little bit smaller. It's 0.448. One more time, our third simulation, we did the same thing. This time we have n equals 50. So we collected 50 mothers at random. We calculated their average height. That's our X bar 1. We collected 50 mothers, calculated the average height, X bar 2. We did this 1,000 times. So that's 1,000 X bars. Then we can average those all together, and that's our mean. So again, we're still at 62.4. There's a little bit difference just because we're simulating. But again, we can see that our standard deviation is even smaller. And in the pictures of the histograms, you can see that the spread, each time the spread is shrinking. It's a little bit smaller than it was the time before or the first time. So, now let's summarize what we've been learning about X bar and how it behaves. So each of these simulations produced an approximated sampling distribution of the sample mean for a particular sample size. What we know for sure, is the population mu, it never changes. That's always what we found right at the beginning, that was 62.5. But each time our estimator X bar isn't going to always be equal to mu. It's going to change from sample to sample. So keep in mind that statistics that come from random samples are also random. This means we cannot know what our sample will produce until we analyze the sample. So one thing we want to note is that each of the sampling distributions at the center of each of the sampling distributions is approximately 62.5. In fact, this is showing us that we have an unbiased sampling method, okay? That's because we were using some random sampling. That is to say that on average, the sample mean is the same as the population mean. This is true for sample sizes, for all sample sizes, as long as we take random samples. So there's a condition we're going to need to pay attention to, that if we use random sampling, we expect that our sampling distribution will be centered at our population mean. Even though our estimator X bar isn't always equal to mu, it's not going to be that far away from mu. And in fact, we're going to be able to predict how far away we can expect that it might be. The estimator from the largest sample size is much more precise than the estimators from the smaller sample sizes. So that's talking about the third simulation is more precise. We had 50 mothers in our sample, and each of the X bars was much closer to our population mean. By sampling more people, we get more information and end up with a more precise estimate. The precision of the sample means depends on the variability in the population, but the more observations we collect, the precise, the closer they are to the actual population mean. And then we can also notice that we saw in the 3 simulations is that the sampling distribution is unimodal and symmetric. So, of course, this was just a an example so we could learn about our X bar. Usually we wouldn't know that our population parameter. Of course, if we did know our population parameter, we wouldn't really need to be using statistics to make inferences about it. But we have to have a starting point to learn. Okay, so we'll be starting section 9.2 and learning a little bit more about the central limit theorem for sample means.